Alright, so today we're going to look at applications of the net change theorem. Alright, so remember we talked about the net change theorem in the previous set, and then we looked at applications where we're given a graph. Alright, so these are ones where I'm given the derivative function. Now I'm still going to use its graph, but I'm going to use the graph on the calculator. Alright, I'm still going to find the accumulated sum of the area, but I'm going to let the calculator do the work for me, unless I'm told to do it by hand. Alright, but I still will probably check my answers graphically because it's a good rule of thumb to always do with these. Alright, so the first application type problem of these, we're going to look at a profit function. Alright, we're given the marginal profit, which is the derivative of the profit, associated with the sale of electric ovens. So X represents the number of electric ovens. Marginal profit, which is the derivative of the profit, is the dollars per oven, the rate of change in dollars per oven. Alright, so it's the rate of change of profit in dollars per oven. Alright, the first question is asking you to sketch the graph of that derivative over a domain 0 to 400. So I'm actually going to use that when I go set up my graph. Label your axes with units and label your y-intercept. And whenever you're doing graphs, you should always do that. Always label your axes with the units they represent and label your starting point, alright, where your graph is starting, your y-intercept. Alright, so I am actually going to use the calculator to help me do this. Alright, so I'm going to go to my calculator. Alright, go to the y equal, which actually my y equals was already up here. Alright, I've already typed in my first one here, negative 0.03x squared plus 9x plus 500. Alright, that's the graph that I'm looking at, the derivative. And remember, I wanted to graph it over the domain 0 to 400, so I'm actually going to go to my window key. And I know I want to graph it from 0 to 400, so that's what I'm going to change my x min and my x max. So 0 is already there. But I have to change my maximum to 400. And then your calculator will actually, once you've typed it in the domain that you want to graph it over, your calculator will actually graph it if you go to zoom and off your page. You have to scroll off your page and you go down to zoom fit. Now it fits it over the x values you've plugged in. So you hit enter. Alright, and there's my graph. Alright, there's the graph of my function over the domain 0 to 400. So I'm going to go back to my notes and now graph it, labeling everything that's important. Alright, so my y-axis, my x-axis. So my x-axis represents electric ovens. This would be the dollars per oven. My rate of change, we start at, if I plug 0 in, I get 500 out, right, if I plug 0 into my derivative. So my starting point's here, my y-intercept is at 500, and then if I look at the graph on my calculator, it goes up, and then comes down and does cross it eventually, and there's my derivative graphed. Alright, the next question. Shade the region of the graph that represents the definite integral from 300 to 200. So I'm going to shade that area above. Alright, and I'm going to use the calculator to do that. Because again, the calculator will help me find it. And show me where the area should be shaded. So it's an accurate representation when I go to graph it in my notes. Alright, so back to my calculator. So remember how we do the integration. I go to second, trace. And then remember, it's the 7th one down. So select 7 and hit enter. Then you type in your lower value, which is 200. Enter. Upper value, which was 300. Enter, and it'll shade the area in. Alright, so that area, so this is the area I'm going to go draw my graph. Going to label it appropriately, and then I know that the area equals 85,000. Alright, so I'm going to put that all out. So the area I know is 85,000. And then shade it, and again, make sure your graph's a representation of what it should be. So about right here, and that's the 200, and about right here was the 300, and that's labeled because it's that 100 that we found the area up. Alright, that's the integration from 200 to 300 of my derivative, which was 85,000. And we'll talk about what it means in a little bit. So that's the part B. Alright, that's all they're asking for in part B. Just wanted to shade in the area that represents that integral from 200 to 300 of my derivative. Alright, next question is asking you to use the fundamental theorem of calculus to find that. Well, I already know what it's going to come out to be. But that's not the important part of this question. The important part is showing the use of the fundamental theorem of calculus by hand, and then you can use your calculator to check your answer. So your answer should come out 85,000. We know that going into the problem. All right, but we're going to show the fundamental theorem of calculus. All right, so remember the fundamental theorem of calculus. I'm going to write down my derivative so I have it. Alright, so in this case, the answer is not important at all, although you should get the same answer that we got before. With this part, if this were a test question, I'm more interested in your showing the fundamental theorem of calculus, how we get to this answer using the fundamental theorem of calculus. Well, the first step in the fundamental theorem of calculus is find any antiderivative of our derivative function. So we usually find the one without a constant. So x raised to the third divided by 3, 9x to the second divided by 2, 500. Again, notation's important. That's just the integral part. At the end, we've got to remember, I still have to take care of my upper and lower limits because it matters. If I pick different numbers, I would get different answers out, right? And so those are the ones I'm using. And so remember, we plug our bigger number upper limit in, and then subtract plugging in our lower number. And what this will find is the net change in profit when sales go from 200 to 300, which you actually already know what that is, but that's what the fundamental theorem of calculus is solving. All right, then the next step that we want to see by hand, we want to see those values. Remember, I'm taking the 300 and the 200 and plugging them into my general antiderivative. And then we'll subtract. Once we're done with the subtraction, it should come out to 85,000. But we want to see these numbers when you're solving it by hand. And so again, this is the process that we're looking for. This is where if you don't show any of this, and you just gave 85,000, well, that's the previous answer, you'll get no points. All right, we want to see what the values are. So when I plug in 300 into this equation, it comes out 285,000. It's a weird 8. And then when I plug in 200, it comes in 200,000. All right, those are the values when I plug them in here. And then when I subtract, I do get that 85,000. All right, so it does check. But like I said, this particular question, the bulk or all of the points were showing the fundamental theorem of calculus. All right, then the last part is interpret your answer. All right, what is that finding? Well, what it's finding is this net change, right? The net change in profit when they increase sales. So the net change in profit if they increase the sales of electric ovens from 200 to 300, and that specific 100 unit change. If I went from 150 to 250, it would be a different change. If I went from 300 to 400, different. It's specific to that change in sales, 200 to 300, that specific 100 ovens going from 200 to 300. Then you will gain exactly, and this isn't exactly, $85,000 in profit. All right, so that's how much profit is achieved when we sell this specific 100 electric ovens. All right, not any 100, specific 100 between 200 and 300. If I picked a different 100, I might get a different amount of profit. All right, so that's an example of the net change theorem in an application. All right, so the next example using the net change theorem. So suppose a study was done in 2011, and it was noted that the number of subscribers to a city's major newspaper was changing at this rate of change, so this would be a derivative, in subscriptions per month. Approximately how many subscribers to subscriptions did the newspaper lose? So we know it should come out negative. during the second 6 months of that year. All right, so time 0 would be the beginning, all right, January 1st, 2011. 12 months later, all right, would be January 1st, 2012. We want to know the second 6 months. So the first 6 months would be going from 0 to 6. The second 6 months would be going from 6 to 12. All right, so that's what we're interested in. How many subscriptions did they lose in 2011 over the months 6 to 12? And so we want to find the net change in subscribers. All right, so again, that's without the prime. There's no prime there. All right, the derivative represents subscriptions per month. The n would represent the number of subscribers. Then we use an integration to solve it. So we're going to integrate from 6 to 12 of that rate of change function. All right, now you could solve this by hand. It's up to you. All right, but most people are going to solve it on the calculator. All right, and so what I want to see, the work that you have to show, right, work is what's important, is I want to see this integration function, because this is what's going to solve the problem. And then once you show me that, you can solve it however you want. So since most students will solve it graphically, I'm going to solve it graphically. But you could solve it by hand. If you solve it by hand using the fundamental theorem of calculus, make sure you show me the by hand method. But I'm going to assume most students are going to solve this graphically. All right, now I'm going to show you what I want to see if you're solving it graphically. All right, so first we're going to go to the calculator and we're going to type in the derivative. That's what we're going to graph. So I'm going to go to my calculator, which I already have it typed in there. I just have to pick it. And I'm going to double check and make sure I typed it in right. All right, so I'm going to unhighlight that one and then go down to my second one. All right, so make sure that that's correct. 500 minus 1400 e to the negative 0.2 x. All right, just double checking, make sure I have it typed in there before I go to graph. All right, so picking that one, that's the function I'm going to graph. Now I'm going to go to my window. I remember my last window, I graphed it from 0 to 400. Well, I don't need to go 0 to 400. All right, this one's just up to 12 months. All right, so I just need to go from 0 to 12. I might go a little beyond 12 just so I make sure I see everything. So I'm actually probably going to graph it 0 to 15. All right, and then I'm going to do a zoom fit and see if that gives me a good enough looking window. I may still have to adjust it from there, but I'm going to start with a zoom fit between 0. And the reason I picked 0 to 15 is because I'm graphing from 6 to 12, and I like to see my axes. So that's why I start with 0. And then I go past 12. All right, and see what the picture gives. All right, so there's my graph. And now I'm going to find my area. So second trace, pick 7, integrating from my lower limit 6 to my upper limit 12. All right, and so there's the calculator's giving me. And so then when you go to show your work, show this picture, all right, a simple sketch on your work. So I'm going to go back and show, all right, what I want to see. So if you're solving it graphically, all right, I want you to at least give me a simple sketch of the graph. All right, so a simple sketch of the graph. All right, the graph came up like this. There was the area between 6 to 12, which was shaded in, and we found that this area was negative 40, or negative 4,020.44. And since we're talking subscriptions, I'm going to round to the whole number, right? A whole subscriber, a whole household. And so there's my answer. All right, that comes out to negative 4,020. I'm going to round to the whole number. And then you should give it with units. So answer the question. How many subscribers did they lose? Well, the newspaper lost. All right, so they lost about, since I did round, 4,020 subscriptions over those 6 months. All right, so that's the answer, right, with units. So that's what that 4,020 means, loss decreasing. All right, and this is the work I want to see. I want to see the integration function, and then if you're solving it graphically, at least give me a picture representation of what the calculator's spitting out at you. All right, let's look at my next example. All right, a glass of juice at room temperature. All right, so room temperature is a cold room. It was 66 degrees Fahrenheit. Is placed at a refrigerator at 1 p.m., so that's time 0. Its temperature, after X hours, is changing at a rate of, so that's the temperatures rate of change in degrees per hour, and the domain goes from 0 to 10. All right, show how it works. Any integral is used. By how much will the temperature of glass drop? Change from 1 p.m. to 5 p.m. So we're looking for the net change, the exact change in my temperature. 1 p.m. represents time 0. 5 p.m., be careful. It's the hours past 1 p.m. That's only 4 hours, right? 1 to 2, 2 to 3, 3 to 4, 4 to 5. All right, be careful there. It's really easy for students to do 5 hours, 0 to 5, or even go from 1 to 5. All right, it's not. Time 0 is 1 p.m. 5 p.m. is 4 hours after that. So I'm looking for the change in temperature over the first 4 hours it was in the refrigerator. So the change in temperature from 0 to 4, the integration from 0 to 4 of that rate of change function. All right, and so this is what, again, the integral that we have to use. So there's my integral that I want to see, and then you may solve it graphically. And again, just give me a graph, a simple sketch, and I'm going to go graph it on my calculator, which again, I already have mine typed in. I just have to go highlight it. It's the last one. I'm going to highlight this one. Alright, and then domain 0 to 10, so I'm going to change my window 0 to 10, and then do a zoom fit and see if that gives me a good enough graph. Alright, so there's my graph, and then we're graphing from 0 to 4. Alright, so second trace 7, lower limit 0, upper limit 4. Alright, and so there it's negative 31.4988. So I'm going to round to negative 31.5. When I go to show my work, I'm going to show this graph. Alright, so go back to my work here. So the graph, and again, it doesn't have to be great detail, just simple. Alright, I know this was its shape. 0 to 4 is what we found. This was the area. Came out negative 31.5. If I round, it was like 0.48 something. Alright, this is the work, and then this is your answer. Negative 31.5 is what that integration, if you solve it by hand, it should come out the same way. And then answer the question. How much did the temperature of glass drop by? Alright, so the temperature dropped by 31.5 degrees Fahrenheit. That's how much the temperature dropped by. And again, include units, right? It's Fahrenheit. That's how much the temperature decreased. Alright, you could use the word decreasing. Alright, the last example. Alright, like I said, this was a big set of notes. Fundamental theorem of calculus is a big concept. Alright, so this is the last example. So we're looking at a marginal cost function. So the derivative of cost in dollars per unit. We also are given the fixed cost is 7,800. So that probably will come into play later on. Fixed cost means that would be the constant. Right? If I don't make any, it's still going to cost me 7,800. So when I plug 0 in, alright, that's how much it's still going to cost me. Or I know that's my constant if I have to use it. It's an initial value. Alright, if you think back to the initial value problems. Alright, but now I can solve initial value problems now using the fundamental theorem of calculus. That's what we're going to get to in this example. Alright, find the exact change in the cost. If the production was raised from 200 to 210, so I want to find how much that will cost me to increase production. We were producing 200 items. We're increasing it to 210, and I want to know what just that change will cost me. Alright, give the definite integral, show all work, check on the calculator. Alright, so give the definite integral, show all work, check on the calculator. Alright, so that means I'm going to solve this by hand. Alright, so that's the change I'm looking for, right? The change in cost from producing 200 to 210. So I'm integrating from 200 to 210 of my derivative. Alright, so the first thing I do is I find my general antiderivative. So negative 0.03x cubed divided by 3 minus 2.5 x squared divided by 2 150x. Right, again, I just took care of the integration. I haven't taken care of the 200 and 210 yet. Next step, find the values at 200 and 210 of my antiderivative. So again, they're going in here. Plug 210 in and plug 200 in. All right, so when I plug 210 into my general antiderivative, it comes out 68985. And when I plug in 200 into this, it comes out 6000. Right? And so the difference is 8,985. And so that's how much cost will change, right? So cost will increase by exactly 8,985. And actually, when we do the fundamental theorem of calculus, we can see that. This is how much it costs to produce 200. This is how much it costs to produce 210, and the difference was 8,900. All right, that's using the fundamental theorem of calculus showing all work. All right, in my next step, I will check on the calculator because the next step is asking me to sketch a graph of the marginal cost function and shade the area that you answered in part A. So this is the check to see if my calculus work, my fundamental theorem of calculus was correct. All right, so I'm going to go to my graphing calculator. All right, that's the last equation that I haven't used yet. And so, oops. All right, and then I will change my window. I know I need to at least go out to 210, right? And I always start at 0 because I like to start on my axes. So I might go 250 and do a zoom trace for 250 because I need to go at least to 210. You could go to 210. 250, I just like to go past mine, and so that's what I'm going to do. I'm going to do a zoom fit. All right, and so there's the graph of my function. All right, now I'm going to find my area. So second trace, 7. Lower values 200, enter. Upper values 210, enter. All right, and then that's what I'm going to, and it does. It checked my answer, so my answer came out correct. So 8,985, and then I show that on my graph. All right, so this would be the units, the x values. This would be the dollars per unit. It does dip down. It doesn't cross, but it comes pretty close and then goes up fairly fast. So there's my cost equation. And then my 200 and my 210 was fairly narrow over here. So 200, because only 10 units. All right, and that's the shaded in area, which came out to the same answer I found by hand. Right, so it checked. Right? For this 10 units, whatever it is I'm producing, so this would be fairly big items, expensive items. So if I produce these 10, specifically the 10 from 200 to 210, I pick the different 10, it would cost me a different amount. But these 10 cost me 8,985. That's the increase in cost, right? The accumulated cost going from producing 200 items to 210. All right, the last problem. Find the cost of producing 210 units. So I just want the cost for 210. All right, there's two ways to do this. You could solve it using the initial value examples like we did in 5.1. Remember, we had initial value problems. But I'm actually going to use the fundamental theorem of calculus to solve this. This is where that initial value is going to come into play, this value here. My fixed cost, which would be my constant, meaning if I don't produce any items, right, because it's fixed, it will still cost me $7,800, right? So if I plug 0 in, the cost should be $7,800. And so I'm given this initial value. Cost at 0 is 7,800. That's my fixed cost, my y-intercept of my cost function. All right, which I don't have, although I mean I could. If you wanted to, you could use this. This is my cost equation, and now I know what the constant would be. The constant would be 7,800. But I'm not going to. I'm actually going to use the fundamental theorem of calculus. All right, I'm going to use my calculator to solve this. If I find the change in cost from producing 0 items up to 210, using my fundamental theorem of calculus, I can solve this. Right? Because I know this value. All right, if I want to find 210, well, I know the cost to produce nothing is 7,800, and then I just find this. So I integrate from 0 to 200, which I already have the function in my calculator. So I just go back to my calculator, and now I do a second integration. So I go second trace, integrate, so pick 7. Now my lower limit 0, enter. My upper limit's 210, enter, and it'll shade all of that in. All right, the upper and lower values, 68,985. All right, that's what I go plug in. All right, and then I solve for the cost of 210, which means I need to add that constant to the other side. And so the cost to produce 210 items is whatever our 60, whatever the value is when I add them up. So give me a second, I gotta add those together. So 7,800 plus 6,8985 comes out to a cost of 76,785. If I can spit out the right number. All right, and there's the final answer. And so you could solve all initial value problems this way if you wanted to. So if you go back and look at the initial value problems we did in section 5.1, all right, you could solve them with the fundamental theorem of calculus in your calculator if you wanted to. You could go back and resolve them using this method, where if I'm given an initial value, I find the net change and that initial value and the value I'm looking for, right? This is what I'm given. This is the one I'm looking for. I integrate between those two values. That'll give me the net change. And then I solve for the part that I'm looking for. All right, plug in the part I'm given, and there's my final answer. All right, so that finishes up the fundamental theorem of calculus. All right, and we will stop there. We're going to do more of the area in the next sections, area between two curves, and then consumer surplus. So we're getting close to the end here. There's only a few more topics left to cover, and then this semester will be over. All right, so we will stop there.